In this video, we're going to look at amplitude modulation, or so-called AM, and its role in wireless communication. Now, amplitude modulation involves multiplying a signal by a cosine. So our objectives are to explore the role of sinusoids in wireless communication and then introduce the principle of amplitude modulation. Now, if I were to take an antenna, as I've drawn here, and I were to measure the signal at that antenna as a function of time, I get some waveform. I'm going to call it x of t. I want to consider the spectrum of x of t. Now, I'm in Madison, Wisconsin, so I know a few things about what I'm likely to see. And I've just sketched out some of them. There's going to be a lot more energy at multiple frequencies here. So I'm starting at 1 megahertz. And just above that, at 1.31 megahertz, I would find a large peak of energy associated with the radio station, WIBA. Now, if I were to go up further at 63 megahertz, I would find the broadcast television station associated with CBS in the Madison area. And then at 88.7, I'd have Wisconsin Public Radio. There'd be energy due to that. And on up further, skipping a bunch of radio stations, of course, at 104.1 megahertz, I'd have Z104. And then up at 550 megahertz would be the ABC broadcast station, channel 27 for television. Different parts of the spectrum are assigned to different purposes. It could be television, it could be radio, it could be mobile communication. In fact, in the United States, the Federal Communications Commission is responsible for allocating frequencies to different uses. And I've just pulled out a graphic showing their assignments in the 300 to 600 megahertz frequency range. You can see there's different purposes. Like this big section here is broadcast television channels, starting with channel 21, and then we have radio astronomy gets a small slice of the spectrum. Radio location gets a slice of the spectrum. There's some land-based mobile communications that are assigned different parts of the spectrum, and so on. Now, how do we interpret this in light of our understanding of sinusoids and the spectrum of signals? This typical spectrum for music is going to be dominated by less than 15 kilohertz, and voice even lower. Now, if you just took something that was in that frequency range, it wouldn't propagate very far. Even if you converted it to an electromagnetic wave, it's difficult to transmit because the frequency is so low. And the other problem is that if I was limited to this frequency range for all my voice or all my music, I would have a lot of trouble with interference. I'd only be able to transmit one radio station, because if I transmitted two, they would overlap with one another. And we've been in that situation where you have multiple conversations in the same room, or people playing different sources of music in the same room. And it's just difficult to understand what is being said or the song that's being played. So we have many signals we're interested in transmitting at the same time that occupy the same frequency range. And the way we do this is through something called modulation. And that's how we assign different purposes to different frequencies in the electromagnetic spectrum. And we're going to look at amplitude modulation, and this is an excellent way to understand how modulation in general works. So we're going to go back to expressing some arbitrary signal V of t as a sum of cosine of different frequencies. And we said that over a limited time range and given enough frequencies n, we could approximate any signal almost perfectly using this type of representation. And then we use this to derive the spectrum of V of t by expanding the cosines into their positive frequency and negative frequency components, and looking at the complex amplitudes associated with each frequency component. So AK is the complex amplitude at frequency FK, and AK conjugate is the complex amplitude at frequency minus FK. So I can draw the spectrum as I've done here. We've got A1 at F1, A2 at F2, and so on up to AN at FN, and then I've got the conjugates at negative frequencies. Well, in amplitude modulation, we define a new signal, x of t, where we take the signal we're interested in, maybe it's voice or music, and we're going to multiply that times a cosine, and we'll assume the frequency of the cosine is Fc. and that FC is much, much bigger than the highest frequency that's present in our voice or our music or whatever it is that we want to transmit. So we can think of V of t as modulating or varying the amplitude of a cosine with time. That's why it's called amplitude modulation. Now this factor of 2 is somewhat arbitrary. I put it in there just so that I don't have to write the 1/2 when I expand the cosine using the Euler representation. So we can look at x of t as being v of t, which was expressed in terms of these complex sinusoids with complex amplitudes ak and ak conjugate at frequencies fk and minus fk. And we're going to multiply that by 2 times a cosine. So 2 cosine 2 pi fct is e to the j 2 pi fct plus e to the minus j 2 pi fct. And with respect to forming this product, we can ignore the sum and just leave it out in front and do the term-by-term products. When you multiply exponentials, the exponents add. So I'm going to have 4 terms associated with the various cross products in these two parentheses. I'm going to have AK, and that's going to show up at frequencies FC plus FK. AK conjugate is going to show up at frequencies FC minus FK. Then AK is going to show up at minus FC plus FK. So that term is this first term on the left times the last term on the right. And then finally, the last term that we'll get when we multiply things out is AK conjugate at frequency minus FC minus FK. So that's the product of this rightmost term in green times the rightmost term in blue. Now this involves shifting the spectrum, because if you think about what's happened here is that AK is no longer at FK, but it's now at FK plus FC. So I've taken where AK was originally in my signal and I've shifted it to the right by FC. And similarly, I have another term where AK has been shifted left by FC. Where it's shifted left is the terms involving the product with e to the minus j 2 pi fct. It's shifted right is where I have the products with e to the j 2 pi fct. It's easiest to understand this using a graphical depiction. So I've restated this equation, I've color-coded all the terms to go with the graph that I'm going to draw. So here I have my original signal spectrum, V of f, and recall x of t is when I use V of t to modulate the amplitude of a cosine with frequency fc. So let's find the spectrum of x of t by taking all these terms. We know that AK is at frequency fc plus fk, so I can start writing out the spectrum. So A1 is going to show up at fc plus f1, A2 at fc plus f2, and so on. Finally, AN at fc plus fn. So these purple terms correspond to all the purple terms in the sum. Now the brown terms, I have AK, and those are showing up at negative fc plus fk. So A1 is going to show up at negative fc plus f1, A2 is going to be at negative fc plus f2, and so on. Finally, AN will be at negative fc plus fn. Continuing doing the other terms, the terms in green are AK conjugate, and those are going to appear at negative fc minus fk. So that's to the left of negative fc. So A1 conjugate is going to show up at negative fc minus f1, and AN conjugate will be at negative fc minus fn. And then in blue, I have terms that are going to appear at frequencies fc minus fk. So A1 conjugate is at fc minus f1, as I've graphed here, and AN conjugate is at fc minus fn. So that takes care of all of our terms. And what we've done is we've taken the original spectrum of V, modulation has shifted it to the right by fc. That's these terms. It's my original signal spectrum shifted to the right by fc. And then I also have the original signal spectrum shifted to the left by fc. This principle allows us to put the information in any signal represented by the spectrum. It allows us to put that in any part of the spectrum we want because we can shift it by FC. So when we multiply by cosine 2 pi FCT, we shift the signal spectrum to be at FC and minus FC. That if I have a spectrum V of F and I multiply by 2 cosine 2 pi FC, I'm going to shift V of F to the right to be centered at FC, and it was from FC minus W to FC plus W. I also shift it to the left by FC. The negative frequencies, it goes from minus FC to minus W and minus FC to plus W. And this is the secret to communication because I can take my voice or my music or my video, whatever I wish to communicate, and I can shift it to a frequency where I have efficient antennas and where signals propagate well through the atmosphere. And it also is a way I can prevent interference between simultaneous transmissions because I can assign one communication to one frequency and another communication to a different frequency. And that's why different radio stations broadcast at different frequencies, and television broadcasts at yet another frequency, and your cell phone yet another.